Morning, everyone. My name is Reza Taghavifard, and together with Professor Andrei Nejur, I'll present our paper titled A Strategy for Decomposition and Fabrication of Volumetric Meshes with Flat Sheet Materials. This research comes from the Laboratory for Architecture, Informatics, and Robotics at the University of Montreal. In computational design, 3D meshes are widely used to model architectural forms, but when we want to fabricate these complex forms from flat sheet material, decomposition is required. For surface meshes, many segmentation and unfolding methods exist. However, volumetric meshes, especially those produced by 3D graphic statics, are much more complex, and current fabrication methods don't address them. Our goal is to close this gap with a graph-based strategy. As you can see in this figure, 3D graphic statics is a form-finding method that generates equilibrium-based geometries. Unlike surface meshes, volumetric meshes capture not only the skin, but also the internal logical forces. This makes them powerful for design, but also difficult to fabricate because faces may be shared by more than two cells. Here we included these two images to highlight the multi-layer nature of the form and to show a case study example where our method is applied. They illustrate both the structural depth and the spatial complexity of volumetric meshes, which are at the center of our research challenge. Our first step is simplification. We eliminate redundant faces while preserving the main load paths. This reduces complexity, saves material, and prepares the mesh for segmentation. We use a weighted priority system based on edge count, surface area, and topological importance to decide which faces stay. In our case study, this led to a 42% reduction in material usage without compromising structural integrity. And this was really important for us because we also needed to preserve the load paths because that's why we are using form finding methods like graphic static. Next, we construct the dual graph. Here you are seeing a simple regular mesh in which a graph-based method are used to unfold it. So in this kind of dual graphs, which is common for decomposition and unfolding, uh, each mesh face becomes a node and shared edges become connections. However, volumetric meshes often include multi-manifold edges shared by more than two faces. To handle this, we apply an edge expansion process, which I will explain in the next slide. Before we segment, we resolve multi-manifold edges. Edges shared by more than two faces, which most graph algorithms cannot handle. We apply edge expansion. For each multi-face shared edge, we create pairwise connections between every incident face in the dual graph, tagging these as expanded edges. This converts an ambiguous many-to-many junction into a set of simple two-face links. So weights and clustering behave consistently. We then weight both standard and expanded edges using dihedral angles in order to have smoother transitions, uh, get lower cost, and topological proximity, a penalty if there are many faces in between around that shared edge. Finally, a Kruskal style growth merges faces across the lowest weight edges. and this yields connected fabrication-friendly segments. After segmentation, as you can see in this figure, we apply an in-plane offset to each face. This offset creates a small distance between neighboring faces so that segments don't overlap during unfolding and fabrication. Where faces should remain connected inside a segment, the remaining dual graph edges are used to generate bridging faces, highlighted in green in the right figure. These bridges preserve continuity and keep the component watertight, while the offset provide clean separation at cut lines. This step not only improves fabrication readiness but also ensures each segment is structurally coherent and easier to assemble later. Here you can see the outcome of our method on the case study. This slide shows the bridge case study and the step-by-step process of our method. First, we identify redundant faces using a weighted priority system. Then we remove those faces, simplifying the mesh while maintaining load paths. Finally, we segment the simplified mesh into fabrication-ready parts. The results are significant. We reduced material usage by 42% and produced 35 distinct flat segments that can be unfolded and fabricated. In conclusion, our framework connects computational form finding with practical fabrication. Future work will focus on detailing connections between parts and optimizing assembly sequences. Thank you for your attention. I'll be glad to take your questions.